Alright, so in this video we're going to look at some questions that link together different topics in this year of physics. So to start off with, we're going to look at linking phase change, or changing between solids, liquids and gases, and electromotive force. So let's just start by seeing if we can remember what some key terminology is. So electromotive force, or EMF, is the electric potential energy transferred to each coulomb of charge passing through a power source, whereas potential difference is the electric potential energy transferred from each coulomb of charge passing through a component. So EMF is increasing the electric potential energy, potential difference is decreasing it. Alright, so let's look at phase change, or state change as you might want to call it. Okay, so I've given you a selection of terms that we can use there. So what I'd like to do is pause the video, see if you can fill in the blanks, and then we'll take a look. Alright, so now you had a chance to do that. So in a substance, all the molecules are attracted to one another via the electric force. And what that means is, if we want to separate them, we're going to have to put in energy, but when we do that, what we're doing is we're effectively storing energy. Okay, so if we want to change a substance's phase from liquid to gas, their separation must increase. You can see it on the diagram there. The separation between molecules is much bigger in a gas than it is in a liquid. So if we want to increase their separation, we're going to increase their electric potential energy, because we're supplying energy to move them further apart. So as I just said, we have to supply energy to do that. We can't increase their electric potential energy unless we put some energy into here, which is why we have to supply, usually in the form of thermal energy, to make this transition. Okay, so that's phase change. Let's now have a look at that in terms of EMF to see the similarities and the differences. So at the negative terminal of a battery, the electron density is increased. So you can see on the left-hand side of the diagram at the anode, what the chemical reaction inside the battery is doing is it's effectively outputting electrons. And that increases the electron density, or the number of electrons per unit volume. Okay, so if we increase electron density, the separation between electrons must decrease. So they're all packed a little bit closer together. And because electrons repel each other, you have to put in energy to pack them close together. So in this case, we're still increasing the electric potential energy, even though we're doing the opposite thing. So this time we're decreasing the separation. And that's because electrons repel each other, whereas previously the molecules were attracting one another. So if we're going to do this, the battery must supply energy, and that's what the chemical reaction inside the battery is for. Okay, so that's some similarities there. Let's move on now to have a look at thermocouples, which we encountered as part of the thermophysics topic, but we can now start thinking them in terms of some of the electricity principles that we've learned. So again, two things I want to check our knowledge of to start with. So electron flow, remember, is when we model current as the flow of negatively charged electrons around a circuit. Conventional current is when we model it as the flow of positive ions moving around the circuit. So in a thermocouple, what happens is electrons diffuse from the high temperature to a low temperature, which you can see on the diagram. So what we can do now is we can also label on here the direction of conventional current. So if negative charges are moving to the right, that's the same effect as positive charges moving to the left. So that's the direction of conventional current. Okay, so if you connect both ends of two different materials together and apply a temperature difference, a current will flow. So we can see here we've got the hot region on the left hand side, the cold region on the right hand side, but we've connected their ends together. And what happens is you get the electrons in the better conductor would flow from left to right along the top, then they'll come down and they'll start flowing through the poorer conductor. So electrons in the poor conductor are still trying to go from hot to cold here, but the better conductor, the electrons are moving or diffusing faster, so we get an overall net electron diffusion going around essentially clockwise in our circuit there. Okay, so now we can evolve this to actually how we use a thermocouple with a voltmeter. So what we've done is we've still got the two materials connected together on the left-hand side, but on the right-hand side, instead of connecting them together, we connect them across a voltmeter. Okay, so thinking about our knowledge of a voltmeter, the resistance of an ideal voltmeter is infinite. We do not want current flowing through a voltmeter. That's why we have it in parallel. So no current goes through it, but it's still there and can take measurements in our circuit. So therefore the net current becomes zero. If you have infinite resistance, no current can flow through you. So what we actually get now is instead of a current going around our circuit, we get a potential difference, because we get a region of very high negative charge and a region of very high positive charge. So there's an electric field trying to make charges move around our circuit. So you can see that on here. So the better conductor, the electrons are going to diffuse from hot to cold and leave that on the negative side. And then that's going to leave a strong positive charge on the left-hand side of the better conductor, which electrons from the poorer conductor will kind of fill in that gap, leaving a positive charge on the other side. So this is kind of what it looks like in terms of charge. Okay, so here are the two diagrams I put up. So we've got the diagram of the thermocouple on the left, and we've got the diagram of how the thermocouple builds up a potential difference on the right hand side. So looking at this example, which is a better conductor, iron or constantan? Well, the correct answer to this is iron is the better conductor here. So if you notice on the diagram on the left, it's the iron that's connected to the negative side of your voltmeter. And you can see that on our diagram on the right, the negative side of the voltmeter is connected to the better conductor. So that's how I know that. It's looking at what the charge is like on which terminal of the voltmeter, then you can identify which is your better conductor. Okay. Next question, what would the potential difference be if the wires were the same material? Well, the answer is 0, or 0 volts more specifically. The reason being that if the two materials have the same conductivity, the net current would be 0. Remember, we only build up a potential difference or have a current because one of them is a better conductor than the other. If their conductivities are the same, we're going to get the net current cancelling out, and we're not going to build up a potential difference across the voltmeter. So what would the potential difference be if both ends of the wire were at the same temperature? Well, again, it's going to be 0, because remember, it was our temperature difference that drives everything in our thermocouple. So that's what gives us the potential difference, that's what gives us the electron diffusion. If there's no temperature difference, there's nothing to cause anything to happen. It's like having a circuit without a battery in it. No temperature difference, nothing happens, and you'd get a potential difference of 0 measured. Alright, moving on to look at some electric heaters and specific heat capacity. So again, linking back into the thermal physics topic here. So specific heat capacity, energy required to change the temperature of 1 kilogram of a substance by 1 degree. Power, the rate at which energy is transferred, or energy transferred per unit time, something like that. Potential difference is, remember, the electric potential energy transferred from each coulomb of charge passing through a component, and in a heater, that's turning that into thermal energy. And current, remember, is the rate of flow of charge. So those are our concepts we're going to be using. So first of all, let's draw a circuit diagram to show how we would actually go about determining specific heat capacity. So the circuit diagram part of it would look like this. So we've got a battery shown there because we've got the two cell symbols next to each other showing a battery pack. We've got an ammeter in series with our heater, so that's the circuit symbol for a heater, and we've got a voltmeter in parallel with the heater. We'd also need our block and a thermometer or a thermocouple as part of this experiment too, and at some point we would need to measure the mass of our block too, but those wouldn't be part of a circuit diagram. Okay, so getting specific, potential difference is 6 volts, current is 2.5 amps, block's mass is 1.2 kilograms, and it experiences a temperature change of 14 degrees Celsius over a period of 5 minutes. So first of all, calculate the energy supplied to the block. Well, this is the equation we need to calculate energy, E equals IVT. Plug the values of current, potential difference, and time measured in seconds in there gives us our energy. And now we know how much energy we've supplied and we know its mass and its temperature change. We can figure out what the specific heat capacity is by rearranging that equation there, plugging our numbers in and giving us the specific heat capacity. It's actually 267 blah blah blah, but 2 sig figs is more than enough here. Okay, so if the block specific heat capacity is actually 220, determine the energy loss of the surroundings and therefore the efficiency of the heater. Okay, so what we can do is, because we know the temperature change and we know the mass of the block, we can actually figure out how much thermal energy was usefully transferred. So that's what I've calculated there. We know how much energy we actually put in using our circuitry measurements, so we can figure out that we've actually lost 800 joules to the surroundings there. And in terms of efficiency, we can use the useful energy transferred divided by the total input energy, times that by 100% gives us the efficiency of 82% there overall. Okay, so moving into phase change instead of temperature change. So we're using the same equipment to figure out the latent heat diffusion of ice. The initial mass of ice was 450 grams, and after 10 minutes there's 200 left. Determine the energy supplied to the ice. So we're using the same equipment, so we've got the same current and PD as before, but we've got 10 minutes this time, again converted into seconds, so fairly straightforward. And then in terms of determining the latent heat diffusion, the first thing we need to figure out is how much we've actually changed phase. So we've clearly changed 250 grams or 0.25 kilograms at this point, and then we just rearrange our equation and then figure out the latent heat diffusion of ice. FYI, at this point, that's actually not the latent heat diffusion ice, but it doesn't matter for the purposes of this question. Okay, so determine how long it would take to completely melt the ice. Well, if we first figure out the energy required to completely melt 450 grams or 0.45 kilograms, we've already figured out the specific latent heat diffusion now, so we can figure that out. And then all we can do is we rearrange our equation for calculating energy, because we know what the energy is and we want to know the time. And that gives us our time there in seconds or minutes, whichever you prefer. So how long would it take to melt the ice and raise it to a room temperature at 20 degrees? So what we're going to need to do is essentially figure out how much extra energy do we need to give it to raise the temperature. Well, we can use this equation. Remember, ice melts at 0 degrees. We can then rearrange the same expression as before, but we essentially add together the energy to change phase plus the energy to change temperature, and then again we get our time. So we're taking about an hour to do this process. Okay, finally, looking at fuses or circuit breakers. So again, let's check some key terminology, some of which we've seen before, some which we haven't. Current, rate of flow of charge. EMF, electric potential energy transferred per coulomb of charge by a power source. Power, rate at which energy is transferred. Resistance, which we haven't had before, is the ratio of potential difference across a component to the current through the component. Right, so let's take a look. So we've got a light bulb, power rating 120 watts, supplied with an EMF source at 230 volts, which is what we get out of a plug in the UK. Determine the current. Well, we've got an equation linking power, current and potential difference. You can rearrange that to figure out what the current is. Easy enough. Determine the rating of fuse required that will break the circuit if current goes 10% above that. So all we need to do is multiply the current we figured out in the last question by 1.1. That figures out the number that's 10% above that. So we'd need a fuse with a current rating of 0.57 amps in this situation. Okay, so a lamp has an effective resistance of 100 ohms. The lamp is connected to a UK main supply with a circuit breaker rated at 15 amps. Determine the current drawn by one lamp. So, as we've got resistance and we know the EMF we get from a UK main supply, we can rearrange this equation to figure out what the current is. Doing V over R gives us 2.3 amps per lamp connected. So that determine the maximum number of lamps you can connect before the circuit breaker will activate. Well, if we do the 15, which is the maximum rating, divided by 2.3 per lamp, we get 6.5. So therefore the maximum we can connect is actually 6, because if we connected 7, it would go over the 15 amps and it would break the circuit and it wouldn't run. And this is one of the many reasons you're told not to plug too many things into one socket in your house. You will overload the circuit breaker and it will trip and it will turn off the entire set of power sockets connected there. Alright, and that finishes these synoptic questions on electricity and thermal physics mostly.